Hello class, returning to the topic of thermodynamics and equilibrium chemistry. Where we left off last time was a discussion of Gibbs free energy. And Gibbs free energy is less than zero, is negative, indicating a spontaneous reaction when delta G is equal to a negative sign. There is one confirmed case where this happens every time. That happens when delta H is exothermic, giving us a negative sign, and when delta S, entropy, is positive, giving us a positive sign for delta S. The reason that this always produces a negative sign for delta G is that it's equal to a negative minus a positive, and that always gives us an exergonic reaction, a spontaneous favorable reaction. This term would always be negative in that situation because T is going to be in Kelvin, giving us always a positive number. On the other hand, for a endergonic reaction, one that is not spontaneous and unfavorable, delta G will be positive when we have an endothermic, a positive delta H, minus a negative delta S symbol. T again is always positive, so this term would be positive. So you'd have a positive minus a negative, giving us a positive. And that would be a system where we are decreasing in entropy, giving us a more ordered system. In example 12, we're going to discuss whether or not the reaction is spontaneous with some information. And we're going to estimate using this information. So first, what we can see immediately is that we have a delta H for this reaction that is negative 1,451.6 kilojoules per mole for the standard state reaction. Remember considering that as being per mole. That gives us an enthalpy that is exothermic, giving us a delta H that is negative. That we can know for sure. What we can estimate is the entropy. Now we're going to first look at phases. On the reactant side, we have a liquid and a gas. On the product side, we have a gas and a liquid. So we have gas and liquid reactants, gas and liquid products. That is inconclusive. We're not really increasing or decreasing a phase in a very obvious way. Amount. We have 5 equivalent moles on the reactant side, 2 plus 3, just looking at our coefficients. On the product side, we have 2 and 4. So we go from 5 moles of reactants to 6 moles of products as the reaction goes forward. And our products being greater than our reactants, that's actually an increase in entropy since we're making more stuff. So we could estimate that the delta G for this reaction, being delta H minus T delta S, is going to be a negative sign for our entropy, rather our enthalpy. So negative minus a positive always is going to be negative. So we can consider this to be a likely exergonic reaction, likely spontaneous. Delta G, in addition to being related to enthalpy and entropy and temperature, can also be related to a equilibrium constant. So we're first going to look at a reversible reaction expression where we have coefficient A of compound A plus coefficient of B times compound B is in equilibrium with the products C and D and their coefficients. This is a reversible reaction arrow. It is not a resonance arrow. Our K equilibrium is always described as the concentration of products divided by the concentration of reactants. When we take this expression and apply it to our reversible reaction expression, what we get is our concentrations of C and D raised to the power of their coefficients divided by compounds A and B raised to the coefficients for their exponents, raised to the coefficients as their exponents. So that is our expression for K equilibrium. We can bring that equation into our delta G by setting it equal to negative RT ln K. That is a negative times a constant times our temperature T in Kelvin times the natural log of K equilibrium, which is our equilibrium constant, which is again equal to the concentration of products over reactants. We're going to now take a look at reversible reactions and chemical equilibria. First, a calculation of equilibrium concentrations from initial concentrations. So in this example, I did some crossing out, but here's what it should say. Example 2, a 0.72 molar sample of PCl5 is heated. At equilibrium, the vessel contains 0.4 molar of PCl3 and 0.4 molar of Cl2. These should all be concentrations. Calculate the value of the equilibrium constant for the decomposition of PCl5 to PCl3 and Cl2 at this temperature. So what we are given, and this is an exercise that you should do every single time for these examples, figure out what you're given and figure out what you're trying to find. We are given initial moles of reactants, and or rather our concentrations, and our equilibrium concentrations of product. And what we're looking for is the equilibrium constant K. We're trying to calculate that. This is a decomposition reaction. Over time, our amount of PCl5 is decreasing, our amount of PCl3 is increasing from 0, and our amount of Cl2 is increasing from 0. So our concentration is, we have PCl5, PCl3, and Cl2 as our headings for the columns in this ICE table. And I like to create a little barrier to show the difference between reactants and products. An ICE table shows us how an initial concentration changes to reach equilibrium, ICE. So at the beginning of the reaction, we have 0.72 molar of our reactant, and we have no products. That is going to go down by a certain amount of X as PCl5 is reacted, which increases our amount of PCl3 and Cl2 by the same amount. At equilibrium, we then have 0.72 molar minus X, and at equilibrium for PCl3 and Cl2, we have X and X. Back in the equation, we are actually given concentrations at equilibrium. The vessel contains 0.4 molar of PCl3 and 0.4 molar of Cl2. So that information is given to us. So now that we have our ICE table, we can set X equal to 0.4 and X equal to 0.4. And then we calculate our equilibrium constant K. That is going to be equal to our products over our reactants. So that's the concentration of PCl3 times Cl2 divided by the concentration of PCl5. We can set those equal to X. So we have X times X divided by 0.72 minus X. Those are our concentrations at equilibrium. And then we can make our substitution. We have 0.4 molar times 0.4 molar divided by 0.72 minus 0.4. That all comes out to be 0.5, and equilibrium constants are unitless. Moving on to discuss the Le Chatelier's principle. In a dynamic equilibrium, if it is perturbed, the system will respond in a way that will reestablish the equilibrium. The position of the equilibrium moves to counteract the change, and equilibrium can be perturbed by changing conditions such as concentration, pressure, and temperature. So we're going to continue our discussion about delta G and eventually compare to Le Chatelier's principle to see how it affects reversible reactions. In example 13, we have a mixture of 1 molar H2 and 2 molar iodine, both gases, which are allowed to react. What are the concentrations of all of the compounds at equilibrium? Again, what we're trying to figure out is what's given and what we have to find. So what's given is initial molar reactants, and we're given K equilibrium, and we're trying to find the concentrations at equilibrium. So here we have H2 plus I2 is in a reversible reaction, with 2 hydroiodic acid. The K equilibrium for this reaction is 49.7 at 458 degrees Celsius. Our concentrations we can provide at the top of the columns, H2, I2, and HI. Our initial concentrations are 1 molar of our reactant H2, 2 molar of our reactant I2, and 0 molar of our product. Remember, no product has been made at this point. The change. H2 is going to decrease by X, I2 is going to decrease by X, HI, however, is going to be increasing by 2x. The reason that's 2x is because the coefficient of 2 comes from our reversible reaction. This 2 indicates that for every 1 mole of H2 that reacts, we are gaining 2 moles of HI. For every 1 mole of I2 that reacts, we are gaining 2 moles of HI. So this increases by double the amount that each of these are decreasing. At equilibrium, we have 1 molar minus X, 2 molar minus X, and 2x for all of our components. We have our equilibrium constant, so what we're going to do is set up our equation and make a substitution. So our equilibrium is going to be equal to the concentration of our products divided by the concentration of our reactants. This time we have a coefficient, so the concentration of HI must be raised to the second power because of that coefficient 2. 49.7, which is provided to us, is then going to be equal to 2x squared. The 2x comes from the table, and it is squared based on the coefficient. So when you have a coefficient, it kind of shows up twice, once inside the parentheses and once as the exponent. So we have 2x squared divided by 1 minus x times 2 minus x. We're going to rearrange and bring the denominator up to the side and the 49.7 down to the denominator. So we have 1 minus x times 2 minus x is going to be equal to 4x squared divided by 49.7. We rearrange to get 2 minus 1x minus 2x plus x squared is equal to 0.0880 x squared. We can set all of this equal to 0, solve with the quadratic formula, and we get x is equal to 0.93. At the end of this video, I will show a full page about how to do this and showing all of my work. After we solve for x, we can then calculate our concentrations at equilibrium, which is what the problem is asking for, by taking 1 minus 0.93, which is 0.07 molar, 2 minus 0.93, which is 1.07 molar, and 2 times 0.93, which is 1.86 molar. Moving on to Le Chatelier's principle and thermodynamics. Before equilibrium, we can set delta G equal to delta G naught plus RT ln Q. So this is before equilibrium. At equilibrium, we can say that delta G is equal to negative RT ln K. That's at equilibrium. But before we're at equilibrium, we can't really use that equation. We have to use this one. Delta G is equal to the standard state delta G plus RT ln Q. So what's going on here? Let's revisit our reversible reaction. Components A react with components B to form C and D. We have Q is equal to the concentration of our products raised to their coefficients divided by the concentration of our reactants raised to their coefficients. Q is the same as K except before equilibrium. At equilibrium, our rates of forward and reverse reaction are the same. At equilibrium, delta G is equal to 0. And at equilibrium, Q is equal to K equilibrium. Before we move on to our next lecture, here's the expanded work to show how x is equal to 0.93 for example 13. And then I will move the page down so you can see the rest.